In the last few weeks, we discussed the notion of complex differentiability in great detail. Just like in the case of real analysis, complex differentiability is tied together intricately with the notion of complex integration. When we say complex integration here, we mean integration of complex valued functions over rectifiable curves. We begin this week by defining integration of complex valued functions over rectifiable curves. Thereafter, we will prove fundamental theorems of calculus for such functions. We will also later on prove, in the next few weeks, we will prove a special version of the fundamental theorem of calculus for holomorphic functions defined on nice domains. It's called the Cauchy's theorem. Let's begin this week by recalling the notion of the Riemann integral of real valued functions defined on the closed interval AB. We'll be defining the complex line integral over rectifiable curves similarly. So, recall that if f is a continuous map on the closed interval AB, a real valued continuous map, then the Riemann integral of f over AB is defined as the limit of the Riemann sums and what do the Riemann sums look like? This is just f of t, maybe I should be a little more careful, tj star tj minus 1, j going from 0 to n, where the limit is taken as the partition size absolute value of p, let me denote it that way, converges to 0. Here P is the partition which is given by A equal to T0 less than T1 less than up to Tn, which is equal to B. And the partition size is the maximum mesh size. It's the max over 1 less than or equal to j less than or equal to n of Tj minus Tj minus 1. There is no need for absolute value. It's Tj minus 1. Right, so one of the most important theorems you would have proved is that this limit indeed does exist, and the limit is then denoted by integral a to b f of t dt. So we are going to mimic the definition here to talk about complex line integrals or complex integrals over rectifiable curves. So I am repeating that we will be defining it over rectifiable curves. So let me set the right setting so that we can define it. Let's start with some curve gamma, which is a rectifiable curve. So let gamma be a rectifiable curve. Recall that means gamma is a continuous map from AB to C, and the arc length of gamma is finite, i.e. this is the case, and the arc length which we have already defined is finite. Let F be a map which is continuous and defined on the image of gamma. So let F be a map from gamma of AB into C be a continuous function. Then for a partition P given by A equal to T0. Remember that gamma is still defined on some interval. So this is a partition of the interval AB. For any partition, we define the Riemann sum. We define the Riemann sum to be summation f of gamma of Tj star times gamma of Tj minus gamma of Tj minus 1, and the sum is from 0 to n. Just like in the, oh yeah, I should have probably mentioned that here as well, and it was here, not hence, I'm sorry. And here Tj star is any element in the interval Tj minus 1 to Tj. You take any element in this interval, this limit should exist. And it's not very different here as well, where Tj star is some element in the interval Tj minus 1 to Tj. So you define the Riemann sum this way. So our first goal is to show that the Riemann sums converge as the partition size P go to 0, and we will define the limit to be the integral of f over gamma. Let me write down the proposition which tells us that the Riemann sums that was written above, it indeed converges as the partition size or the maximum mesh size converges to 0. The above Riemann sums converge as the maximum converge to a complex number, to a complex limit, complex number limit, that's what is being limit of, which is a complex number, complex limit, as the partition size converges to 0. The limit is denoted as integral over gamma f of z dz. Integral over gamma f of z dz. Making it more precise, more precisely, given epsilon positive, there exists some delta such that the absolute value of integral over gamma of f of z dz. Remember that this is a complex number. This minus the Riemann sum, which is given by f of gamma of Tj star times gamma of Tj minus gamma of Tj minus 1. This is less than epsilon whenever the partition size is less than delta. So we could mimic the proof from real analysis. We could have considered mimicking the proof from real analysis, but that's not possible here, because if you recall, when we proved that the limit exists for continuous real valued functions on the closed interval AB, we did use the fact that the real line is ordered by considering the upper limit and the lower limit, the Darboux integrals rather, Darboux sums rather. Here, because the functions take values in the complex plane, we will not be able to use the order property. What we will do is we will work it around. We will use the fact that C is complete and that every Cauchy sequence converges. So rather, we will prove the following. We shall prove that given epsilon positive, there exists delta positive such that if P1 given by say A equal to T0 less than T1 less than or to Tn equal to B be a partition, and if P2 be another partition which is say given by S0 less than S1 less than up to Sm equal to B, be partitions of size less than delta, basically the partition maximum mesh size of P1 is less than delta and the maximum mesh size of P2 is also less than delta, then the Riemann sums corresponding to both j equal to 0 to n of f of gamma of Tj star times gamma of Tj minus gamma of Tj minus 1. This is not very different from 0 to m f of gamma of sk star gamma of sk minus gamma of sk minus 1. This difference is less than epsilon. So we are showing a Cauchy property for the set of Riemann sums, and I'll leave it to you to sit down and check that this property ensures that there is a limit, and that limit is being called the integral of f over gamma. Let's get to proving this particular statement. What do we want to show? We want to show that this difference is less than epsilon whenever the maximum mesh size or the partition size is less than delta. Observation is that the usual trick of going down to refinement works here as well. So if Q is a refinement of P1 and P2, then what do we have? Then the maximum mesh size of Q will also be less than the minimum of the mesh size, or rather it's a refinement. So let's mesh size of P1 comma P2. So if P1 and P2 is having mesh size less than delta, then the mesh size of Q will also be less than delta, right? Keeping this in mind, we will be able to write the above. So let's put the LHS above. Let me write it down once. R of P1, and let's call this R of P2. The Riemann sums here. Then mod of R of P1 minus the mod of R of P2. This is less than or equal to the absolute value of R of P1 minus the R of Q. The Riemann sum written in terms of Q, and the triangle inequality tells us that this is the case. So in case we want to prove such a result, we may assume that we can go down to the refinement and prove that this is less than, say, epsilon by 2 and this is less than epsilon by 2 for small enough delta, and hence we get that this is less than epsilon itself. Therefore, we may assume that we started off with one as being the refinement of the other. So hence we may assume, because of the triangle inequality, that P2 is a refinement of P1. Hence we thus have integers. What are the integers? Say, let's call it m0 less than m1 less than up to mn, such that Tj is equal to smj. So notice that m0 has to be equal to 0 and mn has to be equal to m. These are, so this is to be equal to 0 and this is to be equal to m, right? Because T0 is a, which is basically S0, and similarly Tn is b, which is Sm. So this is 4. So anyway, the point is that we can get hold of integers m0, m1, m2 to mn such that Smj is equal to Tj. Let's now get back to what we are interested in. This is the thing underlined in green is what we are interested in. Let's look at the difference and try to write it down more carefully. We have summation f of gamma of Tj star times gamma of Tj minus gamma of Tj minus 1 minus the sum. So this is going from j equal to 0 to n, and this is the refinement of the first partition, which will be equal to k equal to 0 to m f of gamma of sk minus gamma of sk minus 1. And this is going to be equal to, let's write this as, the first term is going to be the same, let's keep that here, minus the second term will be written in the following manner, j going from 0 to n, and for each j we will write it as a sum from mj minus 1 to mj. So this is going to be the next sum will be from mj minus 1 plus 1 to mj of what? F of gamma of s subscript L times gamma of s subscript L minus gamma of s subscript L minus 1. So as you can see, this is just basically partitioning the partition further into smaller pieces. And if you look at the absolute value of this is the absolute value of this can be written down as less than or equal by using triangle inequality. This is j equal to 0 to n summation, or maybe let me write down the terms. This is going to be f of gamma of tj star times gamma of tj minus gamma of tj minus 1 minus summation L is equal to mj minus 1 plus 1 to mj of f of gamma of sl into gamma of sl minus gamma of sl minus 1. A moment's thought will tell you that if you look at the sum of gamma of sl minus gamma of sl minus 1 from mj minus 1 plus 1 to mj, that is just going to be equal to gamma of smj minus gamma of smj minus 1. But gamma of smj is precisely equal to gamma of tj, and gamma of smj minus 1 is equal to gamma of tj minus 1. Therefore, we can write this as being equal or less than or equal to the indices will be the same, but the term inside, let me write it as L equal to mj minus 1 plus 1 to mj of f of gamma of tj star minus f of gamma of sl. This multiplied by the absolute value of this multiplied by the absolute value of gamma of tj, not tj, it will be sl minus gamma of sl minus 1. Okay, now we are in good shape because f composed with gamma is a continuous map which is defined on a compact interval AB. And what do we know about continuous functions defined on compact intervals in R? They will be uniformly continuous. By uniform continuity, we have of f composed with gamma, we have a delta positive such that absolute value of f of gamma of tj star minus the absolute value of gamma of sl is less than, let me just write epsilon by the arc length of gamma, because as is to be expected that arc length of gamma will just get cancelled off later. The difference is less than epsilon by the arc length of gamma whenever the difference of tj star minus sl star is less than delta. So hence, if we start off with delta as the maximum partition size, then gamma of the tj star and sl star will be in the interval tj minus 1 to tj, which will have a distance of less than delta. Therefore, this condition will be satisfied. Thus, for absolute value of P1 less than delta and absolute value of P2. P2 is a refinement, so in particular P2 will also have the not absolute value, the mesh size of P2 also less than delta. We have the difference, so let me just put an arrow from here. This is going to be less than or equal to epsilon by the arc length of gamma times summation j is equal to 0 to n summation L is equal to mj minus 1 plus 1 to mj of the absolute value of gamma of SL minus gamma of SL minus 1. I'll just rewrite the indices here. This is less than or equal to epsilon by the arc length of gamma times summation k is equal to 0 to m absolute value of sk minus the absolute value of sk minus 1. We have still not used the fact that gamma is rectifiable, if you notice. It's only now that we are going to use the fact that gamma is rectifiable. We know that gamma being rectifiable tells us that the thing inside the bracket is bounded above by the arc length of gamma, which is the supremum over all such sums. And this being equal to epsilon, we do have that given epsilon positive, there is a delta such that the Riemann sums turn out to be Cauchy, and hence there exists a limit, and the limit is called the integral of f over gamma. So we have proved the result, and with the proof we have also given the definition. So we have finally proved the proposition, and therefore we have given the definition of what is meant by the integral of f over a rectifiable curve. Let's now look at some of the properties of the integral of f, which is defined over some curve, rectifiable curve gamma. So let's look at properties. The setting along this entire thing would be the same. Let gamma from a, b to c be a rectifiable curve, and f is defined on the image of gamma into C be continuous. So this is the basic setup we will address the entire problem from. So the first property is about how the integral is defined up to reparameterization. Let gamma tilde from AB is already there, from CD to C be a continuous reparameterization of gamma. Then the integral of f of z dz over gamma, this is the same as the integral of f of z dz over gamma tilde. The limit is well defined up to continuous reparameterization. Let's give a proof of this. Since gamma tilde is a reparameterization of gamma, we have a homeomorphism. Phi from AB to CD such that we have homeomorphism. Such that gamma tilde of phi of t is equal to gamma of t. This is precisely what it means for gamma tilde to be a reparameterization of gamma. To prove that the integral of f of z dz over gamma is the same as the integral of f of z dz over gamma tilde, we just need to prove that given an epsilon positive, there exists some delta such that the integral of say f of z dz over gamma tilde can be approximated by the Riemann sums by partitions over AB. Let me write that down. It is enough to prove that given epsilon positive, there exists delta positive such that if P, say A equal to T0 less than T1 less than Tn equal to B is a partition of AB such that the partition size or the maximum mesh size of P is less than delta, then the absolute value of integral of f of z dz over gamma tilde minus the sum of f of gamma of tj into gamma of tj star rather, tj minus gamma of tj minus 1. This is less than epsilon. What will happen if we do this? We will then prove that the limit, we know that the limit of these numbers as the mesh size of p goes to 0, that is equal to the integral of f over gamma. We have just shown that this property is satisfied by integral of f over gamma tilde as well. By uniqueness of limits, both have to be necessarily equal. So it is indeed correct that it is enough to prove that this property is satisfied. Given epsilon positive, we can find a delta so that the property star is satisfied. But we know that from the very definition of the integral, we know that there is a delta positive, there exists a delta prime positive such that integral of f, such that if c equal to say s0 less than s1 less than up to sm equal to b, let's call this say q, is such that the partition size of q is less than delta prime, then the sum of f of gamma tilde of sj star into gamma of sj minus gamma of sj minus 1, this is bounded by the given epsilon. We will again invoke the uniform continuity of phi. In this case, phi is a map from AB to CD, and because of the fact that it's a continuous map on a compact interval, it's uniformly continuous. Then, by uniform continuity of phi, there exists delta positive such that mod phi of x minus mod phi of y is less than delta prime whenever mod of x minus y be less than delta. So this can be always ensured. Now let's pick some partition. Let P be a partition of AB such that the mesh size of P is less than delta. Then remember that phi of T0 minus phi of T1, that will be less than delta prime. And how was delta prime picked? Delta prime was picked so that the condition here is satisfied. The Riemann sum will be at a distance less than epsilon from the integral. Now let's look at the difference. Then absolute value of f over gamma tilde, I will put the absolute value a little later, integral of f of z dz over gamma tilde minus the sum of f of gamma of tj star times gamma of tj minus gamma of tj minus 1. This is equal to the integral over gamma tilde of f of z dz. Now let's look at the absolute value. This minus, let tj star, so we know that gamma, so recall that gamma composed with gamma tilde composed with phi is precisely equal to our gamma. So by replacing the same here, this is going to be f of gamma tilde of p of sj star, sorry, tj star, and that's going to be gamma tilde of phi of tj minus gamma tilde of phi of tj minus 1. But we have done all the necessary, we have taken all the necessary precautions, and we know that the partition Q, which is given by C equal to phi of T0 less than phi of T1. Also, oh yes, so one very important thing at this point is the exercise, which you should sit down and check. This is actually a basic exercise. Phi is monotonically increasing. You have to use the fact that phi of A is equal to C and phi of B is equal to D. So this phi is very special here. It's not just some arbitrary homeomorphism. it takes A to B, C and B to D, and using the fact that it's a continuous map, the intermediate value theorem can be used to show that it is a monotonically increasing function. It's injective as well because it's a homeomorphism. So therefore, we do have the following property: phi of S0 equal to phi of T0 is less than phi of S1 less than Sn equal to phi of Tn, where Sj is equal to phi of Tj. Notice that we picked our delta prime here in a very special manner. By uniform continuity of P, we have picked our delta to be such that, not delta prime, delta was picked in such a manner that if mod of x minus y is less than delta, phi x minus phi y is less than delta prime. And therefore, we have phi of Tj minus phi of Tj minus 1 is less than delta prime. Since our mesh size or the partition size, is less than delta, and that tells us that, so this is equal to the absolute value of integral of f over gamma tilde minus f of gamma tilde of some Sj star. It doesn't matter what that point is, so long as it's in the interval Sj minus 1 to Sj, and this is gamma tilde of Sj minus gamma tilde of Sj minus 1. And remember how delta prime was picked? Delta prime was picked in such a manner that if we have a partition of size, mesh size, or the partition size less than delta prime, then the integral will be less than epsilon distance to the Riemann sum. This in particular will be less than epsilon. So hence what we have shown is that the difference of the integral of f over gamma tilde and the Riemann sum here is at a distance less than, is a number less than delta. The difference is less than delta, therefore it converges to the same point. Hence, integral of f over gamma tilde, this is the same as the integral of f over gamma. So that opens up the world for us, because we now don't need to worry about which parameterization we are considering while we compute the integral. We can go for that parameterization, up to continuous reparameterization, which will be the most easiest to compute. Let's look at a few more properties. The second property we'll discuss is the behavior when it comes to reversal of paths. Let's prove that integral of f over minus gamma, that is equal to f of z dz. This is equal to minus of the integral of f of z dz over gamma. So to prove this, let us look at the curves gamma and minus gamma. So let gamma be the curve which is defined on AB to C. Then what is minus gamma? Minus gamma is a map from minus B comma minus A into C, given by gamma minus gamma of T is equal to gamma of minus T. Right? This is precisely what the curve minus gamma is going to be. Now let P be a partition of AB. P from T0 Tn be equal to B, be a partition of AB. Then what do we have? Then immediately we have a partition. This gives P prime, a partition given by minus of B equal to S0 less than up to Sn equal to minus of A, where Sj is equal to minus of Tn minus j. So immediately we have one such partition. Now both the integrals, this and this, can be approximated by Riemann sums. So let's pick a delta given epsilon positive. Let delta be such that integral of f over gamma tilde and integral of f over gamma can be approximated, can be epsilon approximated. I'll write it in words by partitions of size less than delta. That means that if there is a partition of AB which is of size less than delta, then the corresponding Riemann sum is epsilon at an epsilon less than epsilon distance to integral of f of z dz over gamma. And similarly, if P prime is a partition of minus B minus A of partition size less than delta, then the corresponding Riemann sum is less than epsilon distance to integral of f of z dz over gamma tilde. Suppose we pick our delta in this manner and let P from T0, so P be as above, with partition size less than delta. Then let's look at integral over gamma tilde, not gamma tilde, over minus gamma of f of z dz. I hope I have not written gamma tilde above, because yes, it was minus gamma very specifically. This is not some arbitrary curve that we are considering. This is exactly this curve that we are considering. Right. So if you look at the integral of f of z dz over minus gamma, and let's look at the integral of f of z, sum of that with integral of f over gamma, this is less than or equal to integral over minus gamma f of z dz minus sum of f of gamma of tj star gamma of tj minus gamma of tj minus 1 plus f of gamma of tj star gamma of tj minus gamma of tj minus 1 plus integral over gamma f of z dz. So we have introduced as a term here, we have added and subtracted a term. Let me keep it. Okay, so I'll just rewrite this as this is equal to the absolute value. Let me first focus on integral of f of z dz over gamma minus the sum of, this is j equal to 0 to n, f of gamma of tj star times gamma of tj minus gamma of tj minus 1. This, before we use triangle inequality, let's rewrite the other term. So this term is taken care of, this term is taken care of. And the next term would be integral f of z dz over gamma minus gamma. Everything else has been the same. We'll just change the term here. Every other term has been retained. This term, however, is going to be rewritten by writing it in terms of sj's and minus gamma. So this is going to be equal to j equal to 0 to n f of minus gamma of some sn minus j star. Remember, j became sn minus j, tj became sn minus j, right? Times minus gamma of sn minus j minus gamma of sn minus j plus 1. So this is precisely what happens. Now let's use the triangle inequality, and the first term is just going to be approximated by less than epsilon because our partition size is less than delta, and the second term is going to be integral of f of z dz over minus gamma minus, now we'll write this as j equal to 0 to n. I'll just leave it to you to check that this is just playing around with indices. Whatever I'm writing just now, this is minus of gamma of sj minus of gamma of sj minus 1. And the delta was picked such that if the partition size is less than delta of minus b minus a, then the Riemann sum will be at a distance less than epsilon to the integral. So this will also be less than epsilon, and hence we have this is to be less than 2 epsilon. So what we have indeed shown is that this absolute value of this term inside can be made arbitrarily small. And therefore, they are equal, and hence integral of f of z dz over minus gamma is equal to minus of integral of f of z dz over gamma. Let me give you an exercise which is the next property. The idea and the techniques used are very similar to what we have done just now. However, I would suggest that you sit down and write down the entire proof so that the idea becomes much clearer. So the third property is let f be defined on image of gamma 1 of AB union gamma 2 of CD, where gamma 1 and gamma 2 are rectifiable curves such that gamma 1 of B is equal to gamma 2 of C. So you should have predicted by now that I am slowly going towards concatenation of these two curves. Then, so this is an exercise. The integral of f of z dz over the concatenation of gamma 1 and gamma 2, this is equal to the integral of f of z dz over gamma 1 plus the integral of f of z dz over gamma 2. So this is a complex number, this is also a complex number. We are looking at the sum of these two complex numbers, and that will be exactly equal to the integral of f over gamma 1 plus gamma 2. So remember that if gamma 1 is defined on AB and gamma 2 is defined on CD, then gamma 1 plus gamma 2 will be defined on A, comma D plus B minus C. It will be in that interval. And if you take any partition there, by going down to a refinement if needed, one can get hold of a partition of AB, and after a translation you can get hold of a partition of CD as well. And using the fact that these two partitions can be used to approximate the Riemann integral of f over gamma 1 and the Riemann integral, the integral of f over gamma 2, one can prove this particular exercise. I'll leave it to you to sit down and write down the details. Let me now do change of variable. This is one definition of the integral of f over gamma which you will usually find in textbooks. So the statement is that let gamma be a continuously differentiable curve. Start off with a curve which is continuously differentiable. Recall that this is continuously differentiable if the limit gamma of t minus gamma of t naught by t minus t naught, where t converges to t naught, exists for each t naught, and the limit gamma prime is a continuous function on AB. These two conditions are satisfied, then gamma is said to be a continuously differentiable curve from AB into C. Then, in particular, it's rectifiable. We have seen that it is a rectifiable curve, and we also know what the arc length is. What the current property tells us is that the integral of f of z dz over gamma, which we have defined already, this is going to be equal to the integral from a to b of f of gamma of t, gamma prime t dt. Recall that what is the right hand side here? If sigma from AB into C is a continuous map, let's say, then integral of sigma from A to B, this is equal to the integral of the real part of sigma from A to B plus the plus I times the integral from a to b of the imaginary part of sigma. So with this definition, the two terms featuring here are simple real valued functions on the closed interval AB, and therefore we can talk about the usual Riemann integral in these cases. So f composed with gamma times gamma prime. This is similarly a continuous function from the closed interval AB into C, and we can talk about the integral from A to B of this particular function. What this property tells us is that that's going to be the same as the integral of f over gamma that we have defined. It's not surprising. In most textbooks, you will find that this is being given as the definition of the integral of f over curve gamma by considering only continuously differentiable curves or piecewise continuously differentiable curves. What we have established with this property is that our definition, more general definition rather, of integral of f over rectifiable curves, that's consistent with those definitions you can find in the various textbooks. Alright, so let's give a proof of this. So given epsilon positive, let's get hold of one partition or delta. Let delta positive be such that if the partition size is less than delta, integral of f of z dz over gamma minus the Riemann sum of f of gamma of tj star times gamma of tj minus gamma of tj minus 1. This is less than epsilon. Let's focus on the second term here, or the Riemann sum here, f of gamma of tj star times gamma of tj minus gamma of tj minus 1. Let's write gamma as equal to phi plus I times psi. So remember now that phi is a real valued function on AB. It's continuously differentiable function on AB, and psi is similarly a real valued continuously differentiable function on the closed interval AB. So we will be able to write this as equal to summation f of gamma of tj star into phi of tj minus phi of tj minus 1 plus I times f. So I'll write this as a separate sum so that I times f of gamma of tj star psi of tj minus psi of tj minus 1. So let's bother about the absolute values later. We can write this term as the sum of these two terms. We will show that as the partition size goes to 0, this converges to integral of f of gamma of t phi prime of t dt in the sense that we have defined earlier. So let's try to have a look at that. Alright, so consider this first term, summation f of gamma of tj star times phi of tj minus phi of tj minus 1. What do we know about phi? Phi is the real part of gamma, which is a continuous differentiable function, which is defined real valued continuous differentiable function on the closed interval AB. So in particular, we can talk about the mean value theorem here, and this is equal to the sum of f of gamma of tj star times phi prime of some sj star into tj minus 1 by the mean value property. The mean value property, where sj star is some element in tj minus 1 to tj. That's good because Now we will write the about term, and that is equal to summation f of gamma of t j star minus into phi of s j star minus phi of t j star times tj minus 1 plus the sum f of gamma of tj star into phi of tj star tj minus 1. My claim is that, so what is going to be the absolute value of this? So this is going to be less than or equal to the absolute value of this plus the absolute value of this. And the first term, by using the uniform continuity of phi, can be approximated. So by uniform continuity of phi, let delta be small enough so that the absolute value of phi of sj star minus phi of tj star less than epsilon. And this term hence can be bounded by, this is less than or equal to summation m times epsilon into tj minus 1, which is equal to epsilon times m into b minus a, where m is the supremum of f composed with gamma over ab. Remember that that's a continuous function, and on compact sets it's going to have a bound, it's going to have an upper bound, and that's what we are calling as capital F. Thus, what have we proved? Therefore, as the mesh size converges to 0, summation f of gamma of t, remember that's the first term that we were considering, right? This term is what we were studying, f of gamma of tj star phi of tj minus phi of tj minus 1, this limit as the mesh size goes to 0. This is equal to the limit as the mesh size goes to 0 of summation f of gamma of tj star phi prime of tj star times tj minus 1. And this is precisely the definition of integral from a to b of f of gamma of t phi prime of t dt. Similarly, one can prove that the limit as the partition size goes to 0 of the second term, 0 to n f of gamma of tj star psi of tj minus psi of tj minus 1. This is equal to the integral from a to b. We have used very crucially the fact that phi and phi prime both are real valued continuous functions. So this is equal to f composed with gamma of t sigma, or rather it was psi. Was it psi or sigma? It was psi. Psi prime of t dt. Hence, integral of f of z dz over gamma was equal to integral of f of gamma of t phi prime of t plus I times integral of f of gamma of t psi prime of t, and that's equal to integral a to b. By consolidating the terms inside, this is going to be integral of f of gamma of t phi prime t plus I times psi prime t is precisely equal to gamma prime t, and that's what we had set out to prove. So let me give you a couple of more exercises in the properties. So this is the fifth property, I guess. Yes. The fifth property is that if f is bounded, if f from gamma of AB to C is bounded by M, i.e. supremum of f of z, where z belongs to gamma of a comma b, is equal to M, then integral of f of z dz over gamma is less than or equal to m times the arc length of gamma. That's going to be a straightforward exercise, so I can sit down and work it out. Another exercise which is very crucial and very important is that integral of Cf plus g over gamma, Cf plus g of z dz. So Cf for C a constant. This is going to be equal to C times the integral of f of z dz over gamma plus the integral of g of z dz over gamma. Here f and g both are continuous functions defined on the image of gamma, and C is some complex number, fixed constant. Okay, let me stop here.